we began with easy case, and now we move on. Yeah, now we move on to oblique incidence, okay? Which means the incidence angle is non-zero anymore. So in this case, we have like just the magnitude of k vectors for incident wave and reflected wave and transmitted wave. And then we also know the incidence angle, right? Theta I is what we determine. But theta R and theta T, we have no information. And this can be determined by applying the boundary conditions. So in order to apply the boundary conditions, what we argued was that the surface parallel component, like KIX, KRX, and KTX must be equal, right? So that's the important thing. And from that, what does it say? Okay, so I think I made a mistake in this slide. I'm sorry. So what needs to be satisfied is that this is equal to this is equal to this. This doesn't necessarily be equal. Okay, so the Z component, maybe I should mark it also. So like here, what's important is that surface parallel component of the wave vector must be equal. And from that, we get these equations, right? So the first equation is this. And the second equation is this, right? And then from this, we know these two important things. One is that reflected angle, reflection angle is equal to the incidence angle. And then the transmission angle and the incident angle satisfies Snell's law. That's what we know. Okay. So now we want to solve this problem in more details. So what we want to do is we split the polarization of the incident wave into two components. So the first component is called S polarization, okay? And then S polarization means electric field is perpendicular to the plane of incidence. So plane of incidence, again, is defined by the K vector, incidence K vector, and the normal vector, surface normal vector. And these two vector determines this plane. This plane is basically the screen plane, right? And then you have an incident wave, reflected wave, and transmitted wave. And then S polarization means that electric field is perpendicular to the plane of incidence. Okay, so S and P are from German words. I'm not sure what exactly that is, but S means perpendicular, P means parallel. Okay, that's what I heard. And then P polarization, on the other hand, electric field is parallel, like lies in the plane of incidence, right? So these two components are basically independent. So anything in between can be written as a linear combination of these two. Okay, so what we want to do is to solve this case and that case separately. Okay, so the first is S polarization. S polarization, again, the electric field is perpendicular to the plane of incidence. So, and then this is Z and this is X. So E is parallel to AY. Okay, and in this case, because we know KI, KR, and KT, what we need to determine is the E and H. And E here has Y direction because it's S polarization. That's what we decided to do. And then when E has a Y has only Y component, then HI can be evaluated by aka EI divided by eta 1, right? So once we determine EI, HI is just follows. There's no ambiguation. And here too, ER also has only Y component, and then ET also has only Y component. This is forced by the choice of the polarization here. Okay, so now you have this. And what else is left? What's left is finally applying the boundary conditions, right? But here, what you need to be careful is that in the normal incidence, your electric field and H field are both parallel to the surface, right? So the only boundary condition you need to apply is that E parallel is continuous, and then H parallel is continuous. And here in this case, electric field, well, H field at least, have surface normal component and surface parallel component. So you need to satisfy everything, like E parallel continuous, H parallel continuous, and B perpendicular continuous, and D perpendicular continuous, right? So these 4 boundary conditions are what you already know, and then you need to make sure that everything is satisfied here. So if you solve it, but here, fortunately, if you satisfy these 2 boundary conditions, like E parallel and H parallel, you will realize that H normal condition is also satisfied. It's I don't want to go into the detail, but that's the case. Like when these 2 conditions are satisfied, then H normal is also, B normal is also continuous. So that's why I have only the 2 of these. And then, so these 2 conditions, the E parallel continuous is just the E field. The incident wave and reflected wave is equal to transmitted wave. And then in case of H, we have these forms, right? But H parallel is what H parallel is this, the X component of the H field. And then if you make all these equal, then we have this condition. We have this condition, right? So these 2 conditions can be solved simultaneously. And the result is that the ratio between the reflection coefficient and reflected electric field and the incident electric field, which is called reflection coefficient, looks like this. And then transmission coefficient looks like that. Okay, and then yeah, so that's what I wanted to say here. So the solution for the P polarization is also the same, but before I move on to that point, is there any question regarding up to this point? So the basic principle is the same, right? We just assume 3 waves: incident wave, reflected wave, and transmitted wave. And although the problem is a little more difficult or a little more complicated, but still what we've done is just applying boundary conditions, right? To determine the ratio between the electric field amplitude. Okay. And the P polarization is the same, as I said. In case of P polarization, electric field is electric field is lies in the plane of incidence, and because we know Ki expression, we know the electric EI, the electric field, the incident electric field. So the x component of the EI is the cosine theta I, and then z component of the EI is minus sine theta I. Okay. So let me graphically express this. So this is basically theta I, and then this is x component, and this is g direction. So this is g component. So the x component is cosine theta I, z component is minus sine theta I, right? And similarly, you can also determine the electric field component for reflected wave and transmitted wave, right? And the same, the rest of the part is exactly the same. Now you have electric field, which are composed of x and z components. Then you can do AK cross E divided by eta. Then you get H, right? But in this case, H should be perpendicular to the plane of incidence, so it only has Y component. Right? I hope everything here is straightforward for you. If it's not, just let me know. Okay. So then what? Then we solve again, applying the boundary condition. And then apply these two boundary conditions again. And then you can solve for reflection coefficient and transmission coefficient. They look very similar. Like if you compare for S case and the P case, they look similar, but actually they are a little different. So if you look at here, eta 2 cosine theta I, eta 1 cosine theta T. Okay, so eta 2 and theta I are kind of connected here, and then eta 1 and cos theta T are connected, right? But if you go to the P polarization case, eta 2 cosine theta T, not theta I, and then eta 1 cosine theta I, not theta T, right? So it's, slightly different. It's almost the same, just slightly different. Okay. So, and then what I want to talk is some of the special angles. Okay, so like in this problem, now for the P polarized waves, we have a special angle called Brewster's angle. So P polarized waves, if you look at the equation here, the reflection becomes 0 when numerator here is 0, right? So eta 2 cosine theta T equals eta 1 cosine theta I, then the reflection becomes 0, no reflection at all. Okay, and then that condition, I just rewrite this condition here, right? And then what can we do? So we can square both sides. Then this becomes eta 1 squared. Cosine squared theta B is 1 minus sine squared theta B. And then here, eta 2 squared, 1 minus sine squared theta T. Okay. And then applying the Snell's law here. Snell's law says that n1 sine theta I is n2 sine theta t. So if you apply that to theta t here, then this equation becomes like this. Okay, and by combining these two parts and then rearranging the terms, we get this relation, right? And then thinking about the definition for eta. Eta was epsilon mu or mu epsilon. I don't know. I always forget like which one is which, but anyway, it's either of these, right? So if you apply these definition, then you ended up having something like this. Okay, and then here we can further simplify this equation because most of the materials are non-magnetic, as I said earlier. Non-magnetic means mu2 is equal to mu1 is equal to mu naught. Okay, so we can basically cancel this out. Then what? Then the numerator is 1 minus epsilon 1 divided by epsilon 2. And then here, denominator is 1 minus epsilon 1 divided by epsilon 2 squared. So, and then this is just basically 1 plus epsilon divided by epsilon 1 multiplied by 1 minus epsilon divided by epsilon 2, right? So cancel it, these two cancel each other out, and we ended up having this. Very simple form, right? And then because sine looks like this, and we can also make it into a tangent form. So tangent theta is square root of epsilon 2 divided by epsilon 1. And then this is equal to n2 divided by n1, right? Remember that the definition of n was just epsilon r, mu r, square root of epsilon r, mu r, and then mu is 1 in this case. So n is just as epsilon, square root of epsilon r. So the ratio of permittivity is equal to the ratio of the index without square root. Okay, so for this condition, you have zero reflection. So one thing you need to keep in mind is that if you think about the tangent function looks like this, right? This is 0, this is pi over 2. So regardless of this value, as long as n1 and n2 are real number, you always have solution, right? So for p polarization, you always have Brewster's angle, which means there's no reflection. And what's happening for S polarization then? In S polarization, if you do the same job, then you ended up having this. Okay, you ended up arriving this relation. And then if you look at here, if like mu1 divided by mu2 is equal to if mu1 is mu2, then there's no solution here, right? So for non-magnetic material, there's no Brewster's angle for S polarization. So Brewster's angle or typically exists only for P polarization. So now, okay. So before then, before we talk a little more about these special angles, this is how it looks. So we defined reflection coefficients, and then transmission coefficients, and then what we really measure in experiment is reflectance and transmittance. And again, the reflectance and the transmittance are the power ratio. Okay, so let's say we have like incident wave and transmitted wave and reflected wave. And then what we measure is actually, because the propagation direction, the overall propagation direction is along Z. So, and the interface is actually perpendicular to the Z. So what we measure is Z component of the pointing vector, basically. So the power flow along Z direction. So in order to obtain that, we have to calculate pointing vector and then multiply cosine theta, right? So this is theta. So you need to multiply cosine theta to the pointing vector in order to get the power ratio propagating perpendicular to the plane. Okay, so if you do that, similar to the previous case, reflectance is just a square, like absolute square of reflection coefficient, but transmission, transmittance has different. So you have not only the square term, but also have these terms, okay, which takes into account the pointing vector calculation terms and also the angle of incident wave and the transmitted wave. Okay. So if you plot two cases, one is the air to water. Okay, so you have ER and UR 1, which means it's air, free space, and then UR is 1, so which means it's non-magnetic material, but epsilon R is 2.25, which means N is 1.5, right? So this is same as air to water incidence. And this is the other way around, water to air. Okay, you shoot light from water to air interface. And as you can see here, for S polarization, the blue curve, you see just a monotonic increase of reflectance. But P polarization, as the angle increases, you have a special angle where you have zero reflection, which is Brewster's angle, as we said earlier. And then the reflection becomes unity. And here the same, like before the critical angle, similar trend occurs. But here, when you shine light from high index to low index, there exists critical angle. And then above the critical angle, you get the 100% reflection, which is called total internal reflection, right? And I'd like to talk a few more things about the total internal reflection here. So we know that, so let me briefly summarize how the Snell's law was introduced. So Snell's law was introduced because K incident X, so if this is the X direction and this is Y direction, I'm sorry, Z direction, and if this is the interface, then KIX is equal to KTX, right? That was, so the K vector, the X component of the K vectors must be equal. That's how you have Snell's law, right? And from this relation, we got what, like the N1 sine theta 1 is equal to N2 sine theta 2, which is basically equivalent. These two are equivalent. And what we want to talk now is that previously what we said was, okay, then sine theta 2 is n2, n1, sine theta 1. And if n1 is larger than n2, then this is larger than 1, right? And then if sine theta 1 is larger than n2 divided by n1, then this entire term becomes larger than 1. So we have no theta 2, right? That was our argument, right? Which is actually true. But, you know, this is not the end of the story, because we know the complex analytic continuation of the trigonometric functions. So what I mean by that is, you know, sine theta is actually 2i e to the I theta minus e to the minus I theta, right? So, and then if you carefully think about this relation, this can be larger than 1, right? There's no problem you have this value larger than 1 if theta is complex, right? So yeah, if theta is, so what I mean by that is, if you look at oh, okay, well, let me, I actually, yeah, I forgot about this slide, but let's talk about this first and then go back. Okay, so yes, so when total internal reflection occurs, which means n1 is larger than n2, then you know, theta I and theta t satisfies this form. And then in this case, sine theta t is n1 and 2 sine theta I, which is larger than 1. So analytic continuation actually allows you to have theta t to be complex number, right? It doesn't have a physical meaning anymore then. But anyway, theta t, if theta t is complex number, then sine theta t becomes larger than 1. You can find the theta t that satisfies this condition. And if this is the case, then cosine theta t, which is 1 minus sine square theta t, and then because sine squared theta t is larger than 1, so cosine squared theta t is smaller than 0, and it's a real number, right? So cosine theta t itself is a pure imaginary number, right? Let me know if this is unclear to you. But anyway, there's no problem just continuing these definitions into a complex plane, okay? So in this condition, when the total internal reflection occurs, sine theta t becomes larger than 1. When the sine theta t is larger than 1, cosine theta t becomes a pure imaginary number, okay? Pure imaginary number. And if it's a pure imaginary number, and now look at these two relations, reflection coefficients, okay? Then cosine theta I mean, this entire thing is a real number. This is also a real number. But here, because theta t is a purely imaginary number, and this is real number, so if you look at here, both cases can be written like this: purely real number plus purely imaginary number, and then purely real number minus purely imaginary number, right? Here the same. Here these two are real numbers and these two are imaginary numbers with same magnitude, right? So then what? Then the reflectance is absolute square of gamma. So there's no problem in calculating this gamma, and that's 1, right? Because if you look at this relation, P plus JQ is, let's say this is a real axis and this is imaginary axis. P plus JQ is like something like this. If this was Q, P, and this is Q, and this is P plus JQ. And then P minus JQ is just like this, minus Q, in the complex plane. So because they have the same complex amplitude, so their absolute value is 1. Right? So what I wanted to say here is that even when the incidence angle is in the regime of total internal reflection, you can still apply like all these equations, and then you can actually obtain the reflectance equals 1. Okay, it's no problem of applying the previously learned equation, even in the total internal reflection case. And another thing that I want to notice is that now if you have a k vector, so kt, transmitted wave vector, and if you look at the surface normal component, which is K2 cosine theta t. And because cosine theta t is purely imaginary, right? It's purely imaginary. So KT, so surface normal component of the K vector becomes purely imaginary too. Which means electric field, if you think about the electric field normal to the surface in region 2, it's not oscillating, but it's just decaying as it moves away from the interface. Okay, and this is different from other cases. Other cases, cosine theta t is a real number, right? Like if you are not in the regime of total internal reflection, then cosine theta t is a real number. And if this is a real number, k is a real number, ktz is a real number, then that means your electric field is oscillating as it moves away from the interface, which is a propagating wave. But here, in this case, electric field is exponentially decaying as it moves away, and this exponentially decaying wave is called evanescent wave. Okay. So if you have a proper picture of total internal reflection, it's like this. You have medium N1, medium N2. You have propagating wave of incident light and the propagating wave of reflected light. Okay, and but here also in region 2, you have field, you have electric field and magnetic field, non-zero, right? And actually that doesn't make any sense, right? I mean, if E and H field are both 0 in region 2, then how can you make your boundary condition satisfied, right? It's impossible. So there is electric field and magnetic field. What's different is that electric field and magnetic field in N2 is no longer propagating along Z direction, but it's just decaying as it moves away from the interface. Whereas in this region, as it propagates, it oscillates. Electromagnetic fields are oscillates. So oscillating electric field gives you the propagating wave, and then decaying electric field gives you evanescent wave. doesn't convey any energy along this direction. It just exists. Okay. And then how do we know this? Well, you can check whether kz is real number or imaginary number. If this is a real number, then e to the I kz gives you oscillation, right? And if kz is an imaginary number, e to the I kz gives you decaying wave, right? IKZ, I'm sorry. That's a little bit too much of a detail, but anyway, I just want to convey you a proper picture about the total internal reflection. Although there are the reflectance is one, but there still exists electromagnetic field in region 2, and that's how it exists. So in this case, theta t is a purely imagined number, or is it undefined? It is defined, but I don't think it's a purely imagined number. It must be a complex number. Because if it's a purely imagined number, so let's say, think about the sign convention. Sine theta is e to the I theta minus e to the minus I theta, right? Divided by 2i. So if theta is just some I times some random number, how can we define ix, for instance? Then this equation becomes e to the minus x plus minus e to the plus x divided by 2i. So it becomes pure. So it becomes purely imaginary, right? But what we want is a sine theta larger than 1, not just an imaginary number, right? So it should be a complex. Okay, so how to use it? How to use these special angles? So one usage, well, this is not a usage, but anyway, it's one interesting picture that you can actually see the Brewster's angle is this. So this is a picture of a window at a taken at the same time. Okay, one without filter, and then second with filter. Okay, so what it says is that when you have a oblique instance, so you're seeing the images of two things. One is the light passing through the window, right? So that if you look at this light, then you can see through the window what's inside. But you also see the light reflected by the window, right? And then in that case you see sky. And then without any filter, you see something like this, like a combined image, the image of the sky and image of what's inside. Okay, and then how to see through? The key point is that realizing that in the oblique instance. So if you think about the oblique instance reflection, S wave and P wave have this type of form, right? You remember. So S wave is always reflected more than P waves. So what's reflected is basically mostly S polarized, right? So if you filter out S polarized light, then you can see through the window. So that's this is what this two example shows. And then this is why you wear a sunglasses with polarization. So here's one quiz, one pop quiz. So you have a car. So this is a car. Okay, so you're driving a car, and then and then you are wearing a sunglasses. Okay, and what you want to do is, like, you know, sometimes you see light reflected off from the road, or sometimes there is a small water pond due to the rain, and then there's a severe reflection happens, which makes your which basically constrain your eyesight. So your sunglasses needs to be polarized along this direction or that direction. So the direction of the bars tells you about which light your sunglasses allows to pass through. So which sunglasses do you want to wear? So if I draw a simplified figure, it looks like this. You are here, and then when around sunset, you have highly oblique instant or oblique reflection, and then you want to avoid these light, right? Because this is not helpful. What you want to see is the light reflected off from the other cars so that you can see the light. So which one you should choose in order to block this component? Okay, well, you have mixed answers. So as I said, when there is a oblique incidence of light, S polarized light is always strongly reflected than P polarized light, right? So you need to filter out S polarization, right? In order to prevent this happen. So here, like in my example, here, S polarized light is, because this is the plane of incidence, right? This is, our screen is the plane of incidence. S polarized light has the electric field along this direction, right? So surface parallel direction. So we need to have sunglasses 1 in order to block the light polarized along this direction, right? So sunglasses 1 allows the penetration of only P polarized light, and then effectively block off the S polarized light. And that's what we want in order to prevent any eyesight constraint. Okay, is this reasonable, or if it's not, just let me know, and I'll give you more detailed explanation if it's needed. And the usage of the critical angle is very famous. You probably heard about the optical fiber, right? So when you shine light, and this is n larger than 1, and then outside is n equals 1. So after certain angle, you have total internal reflection. So no light is going actually out, no energy is actually going out, and only passing through the waveguide. Okay, so that you can efficiently guide your electromagnetic wave along this material, and this is called optical fiber, or sometimes called waveguide. Okay. So leave questions here if you have any. And here's a simple exercise. So what this exercise asks you is like the simple situation where electromagnetic wave impinging from air to a dielectric material. Okay, air to a dielectric material. Determine the Brewster's angle and the corresponding angle of transmission. And then if the wave has S polarization with Brewster's angle, find the reflection and transmission coefficients. So again, the Brewster's angle can be found by using this relation, right? Tangent is epsilon to epsilon 1. And from this we know the Brewster's angle is 60 degrees. Okay. And then when incidence angle is 60 degrees, then by using Snell's law, we know the transmission angle, which is 30 degrees. Okay, if you plug in all the numbers. And now, if you have a S polarization and the Brewster's angle is 60 degrees, so if you apply the 60 degrees to the incidence angle, then you can calculate the reflection and transmission coefficient for S polarized light, which is -1/2 and 1/2. Okay, so this is just you know, you're just plugging in the numbers to the equation, the given equation. So I don't think it requires any you know, time for you to solve. I'm just giving you the answer. But anyway, this is how you apply these formulas to obtain the angle and the transmission and reflection coefficients. And the final topic, I don't think I want to do this today, but I just want to explain what we are gonna do as a final content of this lecture is the layered media. And as I said, we have material 1, material 2, material 3, and then material 2 has thickness of L. And we know the incidence angle and the incident omega. Then what will be the reflection and the transmission? This problem is not an easy problem, right? Because it's not just one reflection event, but the transmitted light undergoes reflection here and the transmission here. And the reflected light undergoes another reflection and transmission. And this light undergoes another transmission and another reflection, and so on and so forth, right? So we can deal with this situation in 2 ways. First way is to track everything. So because these reflection events are very similar with each other, right? Because similar reflection and transmission coefficients are involved. So you can express this as a infinite series. And then you can easily obtain the sum of an infinite series. So that's one approach. Considering these individual events and then making an infinite series and then taking a sum. Second way of solving this is that you realize that there are only a few sets of k vectors are allowed. So let's say this is the incident light, and here it's reflected light, right? No matter how it's reflected many times, all the reflected light have the same k vector, right? And similarly, all the transmitted light have the same k vector. And what's inside is determined by the Snell's law, right? The k vector k2 is determined by Snell's law, the angle. And then reflection doesn't change the angle. So you have only plus g directional k2 and then minus g directional k2, right? So in summary, no matter how many reflection events occurs, there are only 5 waves: incident wave with ki, reflected waves with kr, transmitted waves with kt, and then in the middle you have k2 plus and k2 minus, forward mode and backward mode, right? And then you know that superposition is allowed. So what you can do is you can express everything into just one ER naught e to the minus j, e to the plus j, minus j, kr, r, right? And this ER naught contains everything here. Because all these partial waves shares the same k vector, you can do that. And similarly, you can do the similar thing for ET naught e to the j, kt, r, something like this. And then you can do the similar thing for what's inside, right? And then now you think about it, you have 5 waves. One is incident. So if you take one out, there's 4 waves. So what you need to do is determine 4 coefficients, right? Like E R naught divided by E I naught, which is reflection coefficient, and E T naught divided by E I naught, and also here too, like E2 plus naught divided by E I naught, and then E2 minus naught divided by E I naught, right? These 4 coefficients are unknowns. And then we have 2 boundaries, boundary 1, boundary 2. Each boundary, we have 2 boundary conditions. So we have 4 boundary conditions, 4 unknowns. Problem solved, right? So that's another way to solve this problem. Okay, instead of following all the partial reflection events, we can just making it into 5 partial waves and then applying the boundary condition at the same time. And that's it. Okay. So next time we will learn about how to approach this problem using these 2 methods. And yeah, so this is it for today.